Now it is okay. This can be put as a full screen also, or
Actually,
just
this
in.
is PDF. This is PDF, no, sir.
Okay, okay, okay.
Yes.
No, there were okay. There were some titles also in the beginning. Two slides will be there.
This one, sir. This is the first slide, and
Okay, that
before
means
that,
okay.
this is the
One more should be there.
this is the first
This
one,
is
sir.
okay. This is started. So can I go ahead, Dr. Prasad?
Yes, sir. You can please, sir. You can go ahead.
So today I am going to present on nanostructured aluminum alloys using SPD methods. What is SPD? Is severe plastic deformation. I think AL stands for aluminum alloys. And as I said that Atal, he has given the definition. You people should know what are the definitions before you uh, give any lectures. I think before I start, let me narrate a small story of Swami Ramakrishna. I think how many people may be knowing. I am a student of Ramakrishna school. Once one lady came with her son and requested Ramakrishna sir, Swami Vivekananda's Guruji. She told that, sir, my son is eating lot of sweets. Can you ask him to give us advice not to eat a large number of sweets? Then he told, you come after 1 week. After 1 week, this lady came with her son. Then again, he told, you come after 1 week. Then like that, after 3 weeks, then he told that, beta, you don't eat the sweets. Then this lady got a doubt. Uh, why why you took 1 month, sir, to give the same advice? I was expecting the first week itself, you would have told him that don't eat the sweets. Then Ramakrishna has given the answer to her, stating that I fond of eating lot of sweets, which is not good for health. So for me, it took almost 3 weeks to stop eating the sweets. Now I am in a position to tell him that you should not eat the sweets. So moral of the story is once you wanted to advise some students, if you want to give any advices to others, first of all, you should learn yourself. That is what is the moral of the story. So here, when you wanted to present something to faculty, or when faculty wanted to present their work on the blackboard or whiteboard or through PPTs, you should able to understand. Prasad, can you able to hear?
Yes, yes, sir. Everything is good.
Uh,
Shall I change the
somebody's TV is on, so Ravani Dasari, I think you can ask, you can mute them otherwise.
Rajesh? Please,
Okay, okay.
Rajesh, please mute
Sir,
all other attendees except myself and sir.
sure, sir,
Ah.
sure, sir.
Okay.
And you can see that my name is K. Venkateshwarlu. I think there is a mistake in my name. If anybody can tell about what is the mistake, I will really feel happy. What is that mistake? Can you anyone tell about the faculty members? What is the mistake in that one?
It is
Okay.
Mr. Sir.
Anyway,
It,
Dr. Prasad,
Yes, sir.
the mistake is actually being a South Indian, we write K. Venkateshwarlu. That is not correct. Venkateshwarlu K should be the correct one. Why? Because
Okay.
Venkateshwarlu is the first name and K should be the last name or surname or family name, which is
Yes, sir. Yes, sir.
Karodi. So, but North India people, they write SK Tiwari, son of NK Tiwari. So, or son of SK Tiwari. Then they write the correct way, Sushant Kumar and Srinivas Kumar Tiwari. But if you go to their house, you have to ask which Tiwari you wanted to meet. They will say that Bada Tiwari or Chota Tiwari. So that also gives a problem. So better thing is follow only one system like Venkateshwarlu K or Venkateshwarlu Karodi, And you should be, since I am following for the past 3 decades, I continually keep K. Venkateshwarlu only. And I am from CSIR NAL Bangalore and working for the past 38 years in CSIR. CSIR is the Council of Scientific and Industrial Research. That is a innovative research. Nowadays, they call it as a innovative research. And people, some clever people, they give a lot of definitions, expansions for uh, like CSIR, Council of Scoundrels, Idiots and Rogues. That is not correct. Those who have been appointed by government of India, they're all first class graduates only, and they have done MTechs and PhDs. Then only they are selected as scientists. So next slide, please. Before I go into nanostructured aluminum, what is nanostructured, what is ultra-fine grained material, let me sincerely acknowledge my AICTE training and learning program is called Atal program. And let me sincerely acknowledge Dr. Swami Naidu, principal of JNTU Vijayanagaram. Now I think he is the registrar of college, and Dr. K. Srinivas Prasad. Why? Because K. Srinivas Prasad, whenever we say that our senior one, K. S. Prasad was there, he is from Karnataka. He has done PhD in aluminum grain refinement, and we give a lot of respect to that name. So Srinivas Prasad, Dr. Prasad, you should feel happy that you have a
Sir,
very good.
I am fortunate to have the same name, sir. I should be
Yeah, yeah,
thankful.
yeah. So I feel that you are my senior only. Okay, this is he
Sorry,
is
sir.
a Atal
We are
FDP
very
coordinator and uh, extensively doing good work for conducting this faculty development program. And
thank you
as
very
I
much, sir.
explained earlier, also the faculty development program, all the faculty, you are supposed to attend all the classes, whether virtual or physical, and try to get some of the input from the expert speakers. So, we are not expecting that you will understand 100% what we are telling, but if you can able to get 1% out of us,
Sir,
we are, that is sufficient. Yes, Dr. Prasad. Next slide, please.
okay, sir. Actually,
Now let us understand what is grain refinement using the severe plastic deformation. First of all, before go nanostructured materials, it is basically by many other techniques are available. Solid state techniques is one of the technique is severe plastic deformation. I will go on talking about what are the methods available in severe plastic deformation later, and then finally we'll go to one of the technique which is called high pressure torsion. That is where you achieve nanostructured material. I am very happy to inform you that the machine what is available with us in Basaveswara Engineering College, Bagalkot, this is the first machine or the first and foremost machine in India. We have developed a machine which can do the high pressure torsion. Earlier, one of my students from KLE Belgaum, he has carried out this work and the samples were processed at London. And my postdoc supervisor, he was in USA. So we could able to do some of the good work. We have published extensive papers on this one and high pressure torsion. And also, I'm very happy to inform you that February we are conducting the first time an international conference in Bangalore by Indian Institute of Science. I think those who are interested to attend, you please attend this SPT conference that is called Nano SPT. I have been to 3 conferences. This is the 8th, I think. It is supposed to be 8th severe plastic deformation conference, where uh, leaders like Rulson Value, Professor Terence Langdon, and from Australia, France, many people will be joining for this conference. I think those who are interested, they can go to the net and check that what is that Nano SPD conference in IAC Bangalore in next year, 2023. So I am also one of the committee member in this SPD program, and those who are interested, they can attend this program. So if you are trying to understand the severe plastic deformation, before that you are supposed to understand what is grain refinement, how the grain refinement is taking place. Next slide, please. You can see the word itself, grain refinement. The grain size, Dr. Prasad, can you go for next?
Yes, sir.
So,
Already.
yeah. What is happening is grain refinement by McCartney in 89 or B.S. Murthy in 1999. Every year, there is one paper called International Metals Review. IMR paper is published every 10 years. Suppose you are an expert in that field, you can write the article, and it is supposed to be having references, more than 500 references will be there. It is a bigger paper than almost like your PhD thesis, it will be written. Why? Because you are supposed to has been carried out for the past 1 decade and write a international paper. It for writing an international paper, it takes almost like 6 months, but IMR paper takes almost like 1 year for writing one paper. So when we are doing PhD in 97 2000, Dr. B.S. Murthy now presently is the director of IIT Hyderabad. He has written one IMR paper, International Metals Review papers on grain refinement, where our contribution is depicted there. So when you have so many papers like that, and even though it was published in 1999 and 1989 by McCartney, uh, in 2005, Mishra A from USA, he has given the clear definition of how you are going to get the ultra fine grain structures by using the SPD process. What is UFG? UFG is nothing but ultra fine grains by using the severe plastic deformation. Ultra fine grain size means the grain size is less than 1 micron is called ultra fine grain size. If it is zero point zero 0.01 micron, less than 0.01 micron, those are all called nanostructured materials. So you should have understanding about what is nanostructured materials, what is ultra fine grain structures. So let us see that first ultra fine grains, how they are making. In the step one, you can see that the homogeneous distribution of dislocations. Whenever any material is having, it is having, suppose a material of titanium or aluminum or magnesium or steel, whatever under normal condition, when it is there, so you have a lot of dislocations. Homogeneous distribution of dislocations are there. These dislocations, what happens is, whenever you wanted to process that one, or whenever you want to deform it, these dislocations they dislocate. What is meant by dislocation? They'll dislocate. They are supposed to be in one position. Due to this deformation, they change one place to another place. When they are changing, what happens is you are going to have the step two, where you can get elongate cell formation. When the elongated cell formation, these dislocations blocked by the subgrain boundaries. You can see in the third stage how subgrain formation is. These subgrain formation again break up into elongated subgrains in the fourth case. And finally, what reorientation takes place and subgrain boundaries forms ultra fine grain structure. This is what generally ultra fine grain structure means. This is the unless you understand how it is happening in, there is a big difference between a mechanical engineers and metallurgical engineers. Mechanical engineers, he doesn't bother about dislocations, he doesn't bother about microstructure. You this much, and if I am getting this much percentage of elongation, this much ductility, if I am getting, I am very happy with that one. So that is the tendency of the mechanical engineer. But material scientists are mm, material scientist or a metallurgical engineer. What he does is he try to understand what is happening in metallographically or by using the transmission electron microscope or scanning electron microscope, where you can get more details. This is what I think you people should be knowing. When uh, when you go for an MBBS doctor for a fever, he takes 100 rupees and say that you take a paracetamol tablet. But if you go to a MBBS MD doctor, he will say that he will charge 500 rupees and say that you take paracetamol tablet. So you can feel that why both the doctors are giving the same tablet but charging 100 to 500 rupees. The difference why it is happening. The difference is basically the MD doctor, he understands, he makes a specialization in that one. He understands how it is happening. Only MBBS doctor, he knows only how you should be avoided. That's all. But what is the process in which it is getting getting stopped by the fever? That only MD knows. That's what he gives that fever of crocin or paracetamol, and he charges 500 rupees. So basically, if you can understand this mechanism of how ultrafine grain structures are happening. So this Mishra A et al., they have published a paper in 2005 and given a beautiful explanation of how the ultrafine grain structures are uh, formed. Before that, what we have done is grain refinement. When you are talking in general, like aluminum alloys at the room temperature, when you are deformed, when you are forming, you get a grain size, average grain size of something like 80 to 100 microns. But when you use the titanium and boron master alloys, trying to grain refine those aluminum, and finally you are going to get 30 to 40 average micron grain size. How the average grain size is coming, I think most of the people must be knowing that you can measure this one by using an optical microscope. Suppose in this case, the last presentation, whatever you are seeing is the subcell formation, reorientation of subgrain boundaries and forming a ultra grain fine structure, where left to Bishra A 2005 is written. If I have like this and having a micron bar, suppose 10 mm is equal to 10 microns, I can easily find out what is the grain size of this one. So I know what is the by using the linear intercept method, I can calculate the what is the length L1, L2, L3, L4 like that, and finally I can take the average, and I can also measure by H1, H2, H3, H4, and Hn, and you can measure the average of H1 and L1 plus H1 by 2. It gives the average grain size. So by using the linear intercept method in optical microscope, you can measure the grain size. I think why we should use the optical microscope for doing all those things, it can be well explained by whenever we are talking about the optical microscope. Let us go to the next one and see that. Next slide, please.
Yes, sir. I changed it.
Maybe it is. Now you understand about ultrafine grain materials and what is how to make these ultrafine grains. What are the methods are available? So there are top-down approach and bottom-up approach. There are two things are there. For every, whether in case of materials, it is top-down approach. That is, you take a coarse columnar grain structure, roll it, forge it, or by doing the SPD, you can make nanostructured materials or ultra-fine grain materials. What is bottom-up approach is the by using the powder metallurgy route or by chemical vapor deposition route, you take all the consolidated the fine particles and trying to make a ultrafine grain structure and nanostructured materials. These are the two methods, and these methods are available to make ultrafine grain structures. I think in colleges also, what you find is a top-down approaches means the director or the principal, he takes some decision and he will give it to the HODs, and HODs pass on to the faculty and faculty to the students, so that you make some rules and you can do some changes in the system. Similarly, what is that bottom approach in the colleges or institutes like you? It is you get the ideas from the bottom, that is faculty members or students, and give it to that consolidated those ideas and give it to the HOD, and he will pass it on to the director or principal. So that is called bottom approach. So whether top down approach or bottom approach, that it can be decided by you. In this case, metallic materials, when you are talking, the bottom up approach is a little costlier one, and whereas top down process is a conventional material, rolling, forging, and severe plastic deformation. Now, the new technique has come that whether instead of using the severe plastic deformation, can we make the components directly with the nanostructured materials? This is the question now people are asking. So next time Dr. Prasad will go for 3D or 4D printed materials. Why? Because these are the additive manufacturing techniques where now conventional rolling, forging, extrusion, all these process being stopped by using the additive manufacturing technique. I think next year when he makes some program like this for 2 weeks, he can go for the 3D or 4D printing of metallic materials or PLA or ABS material. Uh, I think you can consider that request to make one more this thing.
Okay,
And
sir.
next slide, please.
Yes, sir.
We are talking about the ultra fine grain structures. Now, what are the methods are available? You have seen. Next slide, please. I think it is a little slow, I think.
Yes, sir. I changed it, but
Now, what we have done is, I'll compile all the things in one slide and try to give explanation for each process how we are doing it. Now, here I can show that why, because we are supposed to have one presentation on severe plastic deformation, consolidated one. So, what is that grain size? What is submicron meter and nanometer range? To generate the grain sizes, we are using the severe plastic deformation technique. Hence, materials can exhibit superior physical and mechanical properties. This is a basic idiom. Uh, One of the scientists who is known as mm, Hall and Pech, there are two scientists who has extensively worked on understanding the grain size influence. They discovered that sigma y is equal to sigma 0 plus k d to the power of minus half. What is d to the power of minus half is nothing but grain size. So whenever the grain size is reducing, I think the yield strength is increasing. And basically, all mechanical engineers should keep it in mind. Metallurgical engineers should keep in mind that it is not the question of UTS or YS. It is the only design purpose YS is considered. Why? Because YS is in elastic limit, whereas in UTS is in plastic limit. Once it is crossed to the yield strength, that is plastic, elastic to plastic region, the material, whatever you are getting, is no use. You can only for the purpose of understanding how much load it can take, that you can go for ultimate tensile strength, which is maximum load by cross sectional area, that is in MPa, Newton per mm square. But here, when you are doing the severe plastic deformation, what are the methods are available? The first and foremost, when we are wanted to discuss, is ECAP. Nowadays, ECAR also has come, equal channel angular rolling. Why? Because conventional rolling process, in fact, we have seen rolling, extrusion, and forging, then SPD methods. They wanted to combine the rolling process. I think you are the first institute which has been made ECAR process. I think the equipment is with you. I think some of them, those who are doing research, they can do extremely good work. I can show some of the slides on what is the material that was taken for ECAR, that I will explain later in some slides. Before that, equal channel angular pressing. The definition itself, you can see that equal channel angular pressing. That means you are having a angular shape in which the channels are equal in size. That is a process called ECAP. What it is happening, the left side first image, if you see, the sample is pressed through a die, in which the die is a single die only, not a partially divided into two pieces. It is a single die when where you have 10 diameter and 100 length. You just press this one with a plunger, which is having a plunger also having a 10 diameter and 100 length. You press this one by shearing method, it goes to another plane, which is a channel which is having the same size of what exactly inlet it has gone. And now by using that outer angle and inlet angle of 90 degrees and outer angle of 90 or 20 degrees, what it is, a shear strain is taking place. And if you go on rotating this sample, again you keep the sample on the top, again you press it, you are going to have repeated this one. How you are changing that one is route BC, route A, that also I'll explain. And after doing this one, what is happening is the structure, initial structure, whatever is there in the initial sample, that is going to be different when you are processing this one. When you are processing, you are producing lot of shear strain in the material. By using that lot of shear strain in the material, the grain size is getting reduced, and finally you are going to get ultra fine grain structure. This is what a simple method of equal channel angular pressing. This is the one people have done extensive work, and now people are also doing a lot of work. And the applications also, whenever 2009 when we went to Russia, we have seen that the application of this process, whether ECAP or HPT or RCS, really what what are the components that is being made by this process. We are thinking only that this process basically for doing a PhD work, and you can come do very nice improvement in the mechanical properties and publish some papers. No, that is not correct. What is happening is these process materials, how engineering components are made. And you can see when we had been to WUFA, that is whenever you talk about severe plastic deformation, Professor Rulson value, he is the man Segal is the first man, and then Rulson value. He is now around 68 or 70 years old, and uh, when he got 60 years uh, celebrations, we had been to Ufa, Russia. Ufa is nothing but a science city of Russia, and we had been to that place. And there is a one lab which is called as severe plastic deformation laboratory. Like a industry, it runs, different methods are used and different components are made. And we have seen practically how the components are being made with this process. If somebody is interested to know about the components, I can list out afterwards. So then another process is called this is having some of the limitations. Why? Because if it is a single die, when you wanted to bring it to other angle, so it takes a lot of now we what we have done, most of the people have done 10 diameter by 100 length only. Most of the papers, whether 80 diameter, 100 diameter, these are the samples they have processed by ECAP. Equal channel angular pressing is generally referred as ECAP process, and people have done extensive work. What we are thinking is now our lab we have made one ECAP die, which is having a 25 diameter by 125 length. This is the we could able to process this one. But die is a split die, it is not a single die. Why? Because single die, if any problem comes, it is very difficult to very difficult to machine inside the die. So what we have done, we have made a split die, and we have done experiments, and it is working very nice. So another process is called repetitive corrugation and straightening, that is RCS process. In this process, what will happen is you can see in the middle diagram, the sample is kept between the anvil of it is having a curve type. And when the large plastic strains are imported into the materials, which leads to the refinement of the microstructure. So initially the size has become corrugation in nature. Then you take two flat dies and press it, and it will become a flat sample, original sample. Again you do the process one direction, and four directions you are having, you can go on changing the direction, and you can get the very grain refinement here, and you can get, and we have shown how the mechanical properties are changed in this process, and I will come into the details later. Similarly, left side, whatever you are showing ECAP process also, the microstructural details we have published, and these are all published work only, by Material Science Engineering A and Materials Letters. These are the papers we have published. And now RCS also we have published in Materials Letters and Scripta Materialia. And whatever the work we have done very clearly shows that what is the good grain refinement it has taken, how the mechanical properties have been changed. The third and most important process is called high pressure torsion. That is, here, what is happening? The shear deformation between a fixed and a rotating anvil without losing the original dimensions. What happens is, if you can see in the center, the specimen is kept, and specimen is something like a 10 diameter into 1 thickness. This sample, when you apply some load, and from bottom, if you can rotate, I don't know whether PDF, I cannot show how it will rotate, but you can see the TM image, the grain size has become to 150 nanometers. That is what after 2 tons, particularly when we have done for aluminum 2 silicon alloy, the average grain size reduced to 150 nanometers. Where is one my 1 that is 1000 microns, so it has reduced to 150 nanometers. This is a only method in which you can achieve nanostructured materials. The today's topic is on nanostructured materials. I think you can clearly see that by using this HPT method, you can really go for a nanostructured material. Other processes are there by mechanical alloying or plasma coating. These methods are used for generating a nanostructured material. And those who are working on friction stir welding or friction stir processing, FSP or FSW, you can see that this is one of the method in which you can get the nanostructured materials. Why? Because whenever you are doing the friction stir welding or friction stir processing, you can generate nanostructure there. That's what whenever any welding is taking place, what you are going to get is the weldment will not break. Only the heat affected zone will try to break. Why? Because you are in the heat affected zone, you get the columnar grain structure, whereas in the weldment zone, you are going to have a nanostructure or ultra fine grain structure. So no cracks will initiate in this one. Only wherever the weak portion is there, like heat affected zone, you are going to have the cracks, and eventually the metallic materials and plastic materials. Nowadays, if you see aircraft also, the even though Wright brothers have invented this aircraft, initially wood they have started. Afterwards, they have gone for titanium, then aluminum, then now CFRP and GFRP material. Why titanium is 4.5 grams per cm cube, and aluminum is 2.73, 2.7 grams per cm cube. I think grams per cc. Uh, Whatever you are doing now, plastics have come 1.9, 1.4, and zero point 0.9 grams per cc. This is what the so that performance will be better. And what is the difference between a metallic material and a plastic material, that you should know very carefully. Why? Because the fracture, whatever is happening in the plastic materials or polymer materials like CFRP, GFRP, these materials, there is a failure called catastrophic failure. Catastrophic failure means the failure happens suddenly without any uh, without any introduction of a small crack. So suddenly it will fail. But in metallic materials, the crack initiates, it propagates through transgranular or intergranular, and finally fracture takes place, which will take almost more than 6 months. So we wanted systems like that. So aircraft system also, even though we can replace some of the material with CFRP, GFRP, but Metallic materials you are going to have without any hesitation. We wanted to say that you have to use the metallic materials for aerospace application. Now their skin material has been replaced with the CFRP. Even though a lot of research work is being carried out, uh, the metallic material research is compulsory and it is being done. Next slide, please.
Yes, sir. Change it.
So what is happening is whenever you are doing any process, let us see that each process, how we are doing. I think I'm not going to explain how the structure is getting changed, how the process is made by doing the animation technique. Directly, I will go what are the work we have done. And for example, we have taken aluminum to silicon and we have subjected to ECAP. ECAP is equal channel angular pressing. Now you can see that optical photo micrograph which is showing as cast Li with a beautiful grain size, and you have the micron bar and you can easily get the grain size of that one, and you can see that the silicon particles how it is distributing. And when we have done this one by ECAP 4 process, and you can see one AFM image after 4 pass at room temperature we have done. You can see that the grain size has been drastically reduced, became to ultra fine grain size. And whatever the particles inside the silicon particles are there, in the center part you can take how it is breaking. So there is a drastic difference between initial stage and after one pass, two pass, three pass, four pass. Each pass we are go on changing the direction of the sample, and you are going to have different shapes, different size of silicon. This is the bar chart showing the particle size of silicon, that reduction due to the ECAP process. And when you are doing a very small size like 10 diameter by 100 length, and in that you are making a small disc of 1 thickness, how do you measure this mechanical properties? So these mechanical properties can be evaluated. I think conventionally what you are doing is conventionally what are the mechanical tests like tensile test or compression test or whatever test you wanted to do, you should have a bigger size. When you don't have a size, a very small size like ECAP samples, even though you can get a small miniature samples, here the technique is called ball indentation technique, which has been developed in NAL. They have already transferred this technology to 4 industries. They have purchased this equipment and it is being used. What they are doing is you apply some load, release the load, again apply the load, release the load. By this, you go on doing like that, and you can easily get the what is the YS, what is the UTS, what is the percentage of all the mechanical properties can be achieved. This process itself, I will show you one method how you can do it. Like if you have a thermal power plant, very big component is there, how you can do by using this BAT test, ball indentation technique, how you can use. So the right hand side, will bottom one is a true stress and true strain diagram we have made for as cast, and all one pass, two pass, three pass, four pass sample. You can see very nicely how the stress levels are increasing, our strain levels are increasing when the material, when the alloy like aluminum to silicon is subjected to ECAP. And this paper was published in Material Science and Engineering A, and we have given the reference number also at the bottom. Next slide, please.
Yes.
Now, here you can see that ECAP process we have done for, I think most of the people, those who are after PhD, when they wanted to go for higher studies like a postdoc position, when I went to University of Southern California, I have taken a lot of the samples. Why? Because I know very well that ECAP they are going to do, and I am involved in severe plastic deformation work only. What I have done is I have prepared the why? Because from NML Jamshedpur we had a lot of facility for manufacturing or making a lot of samples. So we have made all 10 diameter by 100 samples with very good surface finish, like CPAL, commercial pure aluminum, I think most of the people must be knowing what are these aluminum alloys. 1000 series to 9000 series aluminum alloys are available. What is aluminum? First, one series, 1000 series is aluminum, pure aluminum. 2000 series, 3000 series, 4000 series, 5000, 6000, 7000, 8000, 9000 series. What is happening is you are going to add some of the alloying elements to increase the strength of the material and ductility. These are the ductility may reduce, but initially you want to improve the strength. That's what if you refer as 2000 series means aluminum copper system, where if you add 4.5% copper, it is called duraluminum. Most of the uh, aerospace sector, what we are using aluminum 2024 system. What is the 2024 is 2 means copper system is added, and 0.02 means the remaining content of magnesium in that one, and last one is whether it is what is the heat treatment condition, whether it is 4 means T4 condition, whether it is T6 condition, whether it is T1 condition, whether it is a O means 0 means it is a cast product. So by using this LI designation, you can easily find out what is that material. So mostly 1000 series we have taken pure aluminum, that is called commercial pure aluminum. When you talk about commercial pure aluminum, that is 98%, 98.4% aluminum. Remaining what is there, iron and silicon as impurities. That's what it is called commercial pure aluminum. High purity aluminum is little expensive, and why? Because you are supposed to remove that iron and silicon. It is an expensive process, and by doing this process, you can see that commercial pure aluminum. What we have done is we have done with all YS and sigma YS and UTS also we have evaluated. UTS on the left side top three graphs. Why? Because we have pulled at different strain rates. We wanted to understand the strain rate of each material and trying to see that if you are increasing the number of passes, how the strength is. From zero pass, that is if the material is having 80 MPa strength, then suddenly it has increased to 100 MPa yield strength, and it has gone more than 120, 140 MPa, when 130 MPa when it gone to 4 pass samples. So this is the way yield strength can be calculated, and this work what we have done for pure aluminum with 4 pass samples, we have shown TM image also. I think by using that micron bar, which is having something like 15 is 1 micron. So the grain size is less than 1 micron. You can see that any sample, any grain size which is not having more than 1 micron. This is the length or width or height, whatever you measure, this is less than 1 micron. That's what you can generate ultrafine point 0.9 microns. 0.95 microns if it is coming. That is in the case of commercial pure aluminum. Similarly, what we have done is aluminum magnesium alloy we have taken. Why? Because aluminum magnesium is 5000 series magnesium silicon, and 3000 is 2000 is aluminum copper, and 3000 is aluminum manganese, and 4000 is aluminum silicon, and 6000 series is aluminum magnesium silicon, 7000 is aluminum magnesium zinc, and 8000 series is aluminum lithium alloys. I request the faculty who are interested to do research work, they can go for aluminum lithium alloys. Why? Because the research work that is being carried out for the past 1 decade has been stopped. Why? Because the process in which the material it is crack orientation or crack initiation starts, it is completely different. That's what aluminum lithium alloys they have been stopped. Now you can add some rare earth elements and trying to see that whether you can overcome this process. I think those who are doing research, I think recently we have published one paper on aluminum lithium alloys. One is published, another one is under pending. It has been rejected by one of the journal. Now we have gone to Silicon Journal, which may publish in Silicon Journal, which is having 2.3 impact factor. Trying to see that whatever work you are doing, trying to publish in international journals so that people should refer your work. It is not the question of publishing your own work and nobody is citing your work, it doesn't make any difference. It doesn't help also. So what is required is your paper, your work should be cited by somebody else. Then only your citation index will go, H index will go. And nowadays, whoever the faculty name in the world you tell, I can tell the full history of that particular scientist. Why? Because we have the beautiful softwares are available by like Google Scholar or ResearchGate, where we can keep the name. You can find out. In fact, every research scholar or scientist or faculty member, they have given the designation, they have given the number, like cricket, how it is happening. Similarly, in research also, in scientist also, in faculty also, they have given the numbers. So you can find out, and please use the internet extensively. You can get all the information what is available in the world. Some of the patents what are available, which are open in nature, you can develop, you can download those patents and see that what is actually happening. You have to spend some time, kuch पाने के लिए कुछ खोना पड़ता है. This is the proverb in Hindi. Why? Because when you wanted to learn, I think when we did our PhD program, we used to go to the library and get the papers xerox and keep in box file. And nowadays everything is available on the net. If you are having a internet, good internet, Scopus Index journals, whatever journals are available, you can download the papers and keep. If you should able to know that if you don't have the reference paper, you are not getting. There are some library people which are available in the internet. They have one consortium. Once you make a request, within 24 hours they will send that paper. That is also possible. So there are many ways in which research work can be carried out. I think I can go on giving the lot of examples. When you write an international papers or whatever the work you are supposed to do it, mm, uh, how you should be published, those things I can talk on for another 1 hour. So here, basically, when you are doing for aluminum magnesium alloys, what we have done is we go on increasing the magnesium content, 1%, 2%, 3%, 4%, 5%. Go on adding the magnesium and see that how it is, the mechanical properties are changing. And what we have found is after 4% magnesium, there won't be any much changes. Why? Because whatever the precipitates they are forming, Mg2Si or Al4Mg precipitates are forming, they don't have much influence on the mechanical properties of 5% or 4% magnesium content. So most of the people restrict this aluminum 4.5% magnesium content only. So we have taken aluminum 3 magnesium, which is exhibiting a superior properties when you consider the ductility and the strength. So this material we have taken. Why? Because what we wanted to do is not only aluminum magnesium alloy, we have added some of the scandium rare earth elements to this one, and trying to see how it improvement can takes place. And we have taken the pure aluminum magnesium alloy, and we have passed one pass, two pass, three pass, four pass. And you can see that the middle one, the mechanical properties, how they are increasing by YS versus yield strength and UTS. Both the things we have evaluated. And after passing for four pass, we have taken the TM image and trying to see that whether the grain size has been reduced or not. You can see that the grain size is drastically reduced, less than 1 micron, whereas the dislocation fringes can be seen. I think in the left right image you can see very nicely the dislocation, and you can get the distance between each dislocation also you can find out. By this one, we have studied and we got a research project on from Aeronautical Development Research and Development Board, and extensive work was done on aluminum 1 magnesium, 2 magnesium, 3 magnesium, 4 magnesium, 5 magnesium. Not only that one, we have added to some scandium content, all 0.2%. Why? Because we have started using 0.2, 0.3, 0.4, 0.5, 0.1 to 0.8, scandium. We found that 0.25% scandium is sufficient. Why? Because the mechanical optimized mechanical properties are being achieved in zero point 0.2 scandium, 0.25 scandium only. And by using the ball indentation technique, we could able to develop all the mechanical properties. It has been depicted in the left bottom third image, and the mechanical properties whatever we have achieved in as cast condition of aluminum magnesium alloy with different magnesium content, it has been given in the last image mechanical properties aluminum magnesium alloy in the as cast condition. So next slide, please. This also has been published, and you can see that I have given the reference of the publication. Next slide, please.
Yes. I changed it.
And I wanted to show you the TM images, particularly when you are referring any, you have reduced your grain size and you are achieving mechanical properties extensively, you are supposed to do some TM images. And you can see here on the top image, aluminum, commercial pure aluminum with the two passes. Still, you can see that even though grain refinement has taken place, you can see some of the grains are elongated in nature, and this elongated nature, when you have gone for 4 pass, you can see that it has been reduced to, I think this image, I think bottom one should be four pass image, where you can see that grain sizes have been almost uniformly becoming a round in shape, not exactly round, but similar to round shape. It has become the columnar grain structure. Columnar structure is being changed to equiaxial grain structure, and which is less than 1 micron. You can see from the micron bar also. This is the work we have done for TM, and these are all work is published. Next slide, please.
Yes, sir.
And what we have done is we have trying to add scandium content, as you told, as we have seen that aluminum 2 scandium master alloy is available, where we can use aluminum 0.25% is sufficient when you are adding. That means any alloy, if you take aluminum, magnesium, silicon, aluminum, zinc, magnesium, any alloy, if you take, if you can do a 0.28% of scandium is sufficient. But aluminum scandium is available in the master alloy form of aluminum 2 scandium. This is a master alloy which is available. So that sample itself we have taken and trying to do the ECAP process, and after 4 passes we can see that the grain size is drastically reduced. At higher magnification you can see that the grain size is still reduced. That is almost like 15 is equal to 200 nanometers. So this has been drastically reduced the grain size. And similarly, we have done with aluminum 3 magnesium alloy after 4 passes. Generally, what happens is after 4 passes, if you go on doing with the 5 process and 6 process, there is no use. This is the one Australian paper. You can see that they have continuously did for 8 passes, and they found that after 4 passes, there is no much difference. So everybody is restricting to 4 passes only. And when you are doing any grain refinement studies, trying to understand if you go on reducing the grain size according to Hall-Pitch equation, the grain size reduction is influencing the yield strength. That means the yield strength is enhancing when the grain size is reducing. Can we go on reducing the grain size like that? So, Professor Atul Choksi from IAC Bangalore Metallurgy Department, what he has done is he has taken nickel and aluminum material, copper material, and he has done extensive studies, go on reducing the grain size by powder metallurgy route and by processing of this method, severe plastic deformation. What he found is after grain size of 20 nanometers, there is no much difference. In fact, grain boundary sliding is taking place. In fact, each grain, when you're having the grain sliding takes place, so there won't be any improvement in the yield strength. Only thing, the ductility can be improved. The size will be optimum size you can get at 20 nanometers. So the people have restricted that. Okay, I can go up to this size, and there after this, even if you reduce the grain size, also there is no effect. This was the work carried by Professor Atul Choksi, and he is one of the key member on IAC Bangalore and on severe plastic deformation, who has worked with Professor Terence Langdon in USA, where he has done his PhD on nanostructured materials and ultrafine grain materials. Mm, uh, this is the one case where we have done that extensive TM work. Let next step, next image, please. Next slide, please.
Yes, sir. Yes, sir.
So what we are trying to understand is we have seen the aluminum 2 scandium, aluminum uh, magnesium Li, 3 magnesium Li with different positives. And you can see we have studied the TM images of aluminum 2 silicon Li also. So we are supposed to understand here you can see that 2000 nanometers is the size where you have almost like a 200 20 20 30 uh, size. So if you can put that one in the micron bar and trying to see the average grain of this will be less than 1 micron average grain size. The particle size also can be measured. And if you don't have the measuring technique like this, what is advised is Image J, one software is available in the internet, which is freely available, open source. One Image J processing software is available. In that, you can go directly, you can take one image and you can measure E volume fraction and size, particle size also. What is the average size? What is the average length? What is the average width? All the things can be measured by using a Image J software. I think right side you can see that the dislocation loop is happening, dislocation pileup is happening. Why? Because you should understand that how the dislocations are moving in this one. Suppose you have a silicon is there. So what is happening is when you are having any material to be deformed, or when you are doing any ECAP process or anything, what is happening is when material trying to process, when you are trying to move the dislocation, if the precipitates comes, they stop the dislocation movement so that the if you can understand the what is hardness is resistance to deform indentation. Similarly here, when the precipitates comes, so this dislocation cannot move. The dislocation can that is the Orvan looping it is called. Whether that is forming or whether the precipitate is getting cut and this dislocation is moving, those details can be studied by using this transmission electron microscope. I think this also has been published in 2010. You can see our paper for more references on aluminum 2 silicon Li. Next slide, please.
Yes.
So we have done the extensive work on aluminum silicon, aluminum 2 silicon, aluminum scandium, aluminum magnesium alloys. This is the typical processing technique used for evaluating the mechanical properties of when the sample size is very, very small, or when the sample you are unable to move it to, suppose a pipe is there and you cannot make that pipe. You have to go to the industry, you have to do the in situ testing and find out what is the yield strength, what is K value, what is N value, all mechanical you want to evaluate. This is a simple technique which is called ABI, that is automated ball indentation system. I think people should appreciate that they have made a extensive research work on this one. You have evaluated by loading and unloading, that is converted to true stress and true strain diagrams. And you can see there is a lot of research work was been done, and finally they have come to a with one Jucom Bangalore and NML Jamshedpur, both together they have developed this machine and they have supplied to 4 industries. And from this technique, you can evaluate all mechanical properties. A software is prepared, generated, and when you apply loading and unloading technique, you can evaluate. Those are all processed and estimated. What are the K values? What is the N values? What is the YS? What is the UTS? What is the hardness? Everything can be measured by using a simple technique called automated ball indentation technique. I think I appreciate if some of the people can purchase this such type of equipment. It will be very easy. Why? Because when the sample size is very small, you can do by using this microscope also. You can use such type of when large pipes are there in situ and you want to do also, you can use this type of ABA technique. Next slide, please.
Yes.
And I don't know how many people are interested about aluminum alloys. Before going to the a high pressure torsion in detail, let me explain what are the material requirement for CSIR NAL till 2025. This is the last year we went to Delhi from all aluminum manufacturers in India like Balco, Nalco, Indalco, Malco, HAL, NAL, ISRO, all the people we went and there was a presentation by every one institute, one presentation. I am very happy to inform that from NAL, I have went for this meeting and presented. Of course, the requirement I will show very quickly, but this requirement is very small when you compare to the requirements of ISRO and other space organization of aluminum consumption. So the requirement is very small when you compare with our laboratory needs. I'll quickly go through these slides on what are the material requirement for CSIR NAL. I think I request Dr. Prasad to go little fast in this one. Show that
Yes, sir. This is
show that what are the material requirements CSR NAL, particularly on aluminum alloys. You can see here we are doing LCA Tejas aircraft and fin and rudder assembly is made of aluminum alloys and what are the alloys. I am going to show you what are the materials specification and what type of form, whether it is a forged or stock or bar type. This is uh, only I am giving the material specification. At the end, I will show you that whatever the total quantity is required. Next one is
yes,
so this is LCA Tejas aircraft. What is aluminum alloys required and civil aircraft systems like we are doing for Saras aircraft and yeah, RTA regional transport aircraft. What is the material we should use? 2124, 2024, 6061. You can see that the T6 condition is being used on 2024. What is that heat treatment cycle they have given? All materials with what are the, whether it is sheet form, extrusion form, or rod or stock form, all are given. Sheet metals thickness used in this one, 0.6, 0.8, 1.2, 1.6, and 2 mm. In general, I think most of the people, you must have a record that the sheets, whatever being used is 1.6 mm in general for all aluminum alloys. Next slide, please. This is for Tejas and aircraft. I think what is the quantity we required? We have written that per set how much is required. 96 kgs we required, and bars and forged stock also what is requirement we have given. Next. So the total material requirement is 6.25 tons only for this purpose. Next slide, please. And for this material, we are almost having a 1,785 kg material is required if you wanted to make. So total material required till 2025, we have estimated around 450 tons. I think the quantity, whatever we are showing here is, you should not feel happy that. And civil aircraft programs like Hansa, where we have new generation we have developed where aluminum is having nowadays aluminum quantity is getting reduced and it is almost like the quantity requirement is 9 tons only and these are the aluminum billets or sheets or extruded products and what is the quantity we required we have shown here. Then is the cnm is National Aerospace Laboratories with Mahendra. We have 5-seater aircraft we have developed and this one the billet sheets and extrusions whatever requirement is there for another 2025 is almost like 1.1 ton only. So even if I have this RTA regional transport aircraft where 70-seater aircraft is being made and the material requirement is 180 tons. Requirement is 180 tons. And in summary, if you have different types of aircraft system like LCA Tejas, that is, I think how many people must be knowing that government has given an order for HL, ADA and NAL to manufacture this light compact aircraft. Light compact aircraft is a replacement of MiG-29 and MiG-20 aircrafts which are generally made by the Russian company. Now, light combat aircraft is made by HAL, and we have a lot of contribution in this one. And this is the indigenously developed aircraft system. Nowadays, if you can see the television, now almost all fighter aircrafts are made with Tejas only. Now government has given an order for making such 70 such aircraft. A break here.
Sir. Okay, sir.
We'll come back after 10 minutes on high pressure torsion on aluminum silicon and aluminum silicon scandium alloys. I
Sure,
think
sir.
we'll stop here. Okay. Can you ask them to come after 10 minutes?
Yes, sir. I request all the participants to come back after 10 minutes so that the part 2 session will be continued by our experts, sir.
Okay. Thank you very much. Thank you.
Thank you, sir. Thank you.
Hello,
Hello, sir.
Dr. Prasad.
Welcome back, sir, to the part two of today's session.
Yeah,
Uh,
yeah. Thank you very much. Welcome back after commercial break for 10 minutes. Those who are interested, I think we are virtual mode. Many of the faculty people, they are very intelligent, and they put on the computer and put off the mic system, and they do their own work. So this is the advantages through virtual mode. If it is a practical mode, you are supposed to listen the whatever the speaker is presenting. Let us see that what is the work that we have carried out on aluminum silicon and aluminum silicon scandium alloys. It is not on the question of silicon content, and silicon with 0.25%, 0.2% scandium we have added in this one. I think whatever we have done is everything we have done with in our laboratory only. And high pressure torsion, that means you are using the pressure something like 4 to 5 GPa pressures you are using, and by doing the torsion you are going to get nanostructured materials. If you see the left side before HPT, how the sample looks is like a coin. It's a coin of 25 paisa coin like that, which is having 10 diameter and 1 thickness only. After HPT, when you are applying such a high pressures and rotating the bottom anvil, I think now I cannot show the video clips. You would have appreciated that how we are doing this video of mission video clips on high pressure torsion. You can really appreciate this one. You can rotate with a quarter ton, half ton, 3/4 ton, 1 ton, and up to 1, 2, 3, 4 tons, 5 tons also you can do it. I think after 5 tons, there is no much difference in the mechanical properties. So who are all doing on high pressure torsion, they restricted their experiments with 5 tons only. Why? Because most of the alloys after 5 tons, there is no much difference in the yield strength and ductility. So understanding this one, let us understand by using this HPT method, you can achieve the yield strength of something like 1000 MPa. I think aluminum alloys, if you are getting around 350, 400 MPa after heat treatment, after ECAP, that itself is a great news. But getting a 1000 MPa is a really great news, and we after we got these results, repetitive results, we got it. We thought we'll present this one to one of the sponsoring agencies like ARNDB. Why? Because we belongs to aeronautics structures, aeronautic boards. So we applied for this one, and we have shown very nicely that this by using this HPT process, whatever material you are talking, aluminum silicon or aluminum magnesium or aluminum magnesium scandium alloy, we can achieve the mechanical properties of 1000 MPa yield strength. But the question it was asked is, when the sample is only 10 diameter and 1 thickness, where you are going to use in the aerospace. So humble request to all the faculty members is, whenever you are applying for a research project, please see the what the sponsoring agencies is looking for. It is not like what is the expertise you are having. We have a good experience on high pressure torsion, but even though we have a lot of interesting results, when we presented this one, they have rejected our proposal. Then we thought that okay, this is not the case. When we wanted to have some sponsoring agency funds from sponsoring agency, what is required is you should understand the what their requirement is. So we have gone for detailed uh, studies on what is the actual thing, what type of projects they are doing. Then we found that on super alloys, they are doing a lot of work on super alloys, nickel based super alloys, where you can have the creep data. If you can develop some of the machine and do the creep data generation, it is very useful. So we have applied that project, and 1.8 crores we got. So it is not the question of fundamental studies. Yes, you wanted to do, you are having a AICT, DST. That if somebody is interested, I don't know whether time permits, I can present that work also, which is research proposals, what type of research proposals can be presented, and how do you get funding. Those details I can give. Now you can see that after this processing of high pressure torsion by severe plastic deformation, which is developing a nanostructure. Next slide, Dr. Prasad. Uh,
Yes.
Next slide. That is after high pressure torsion. I think this is the video. I don't know whether it can work or not. I don't know whether it is in PDF mode. It will not work.
Not
This
working,
is,
sir.
it will not work. I think I cannot show, but this is the controlling panel where we are having. This is already industry. Uh, uh, Earlier one. Can you go to earlier one?
Yes, sir. HPT.
HPT image, you can this one you can see that the control panel is there, where you can move the upper annual movement, lower annual, what are the rotation you can make it. This is a beautiful compact model what we have used. This is based on our design. One of the agency, they have manufactured this one, and it is working very nicely. It is kept in Basaveswara Engineering College. Recently I had been to that place. Why? Because whatever we have done in London, we have compared some of the same material we have used here, and the results are almost coming same. So whatever the machine we have developed is extremely useful, and you can apply the pressures up to 5 GPa pressures. Only thing, the size of the sample is very, very small. Next slide.
Yes.
So when you are doing the high pressure torsion on aluminum 2 silicon 0.25 scandium Li, in as cast condition, you can see that the grain size is almost as cast condition. I am talking, not in the processed condition. It is in as cast condition. It is almost showing like 25 to 30 microns is the average grain size. Where you can see that due to scandium emissions, the refinement also has taken place. This is uh, actual. When you see this aluminum 2 silicon Li, this is without scandium emissions, and with this without scandium emissions, you can see that right side by using the ball indentation technique, or we have taken directly the specimen and we have evaluated the Vickers hardness. I think how many people must be knowing that micro hardness. When you are talking about micro hardness, it is based on HV zero point 0.5 or zero point 0.2. That should be subscript should be subscript should be used. That means what is the load you have used. I think what we have shown here, HV is not the correct one. HV zero point 0.5 or zero point 0.2, it should be specifically mentioned. Why? Because when you are nowadays, I am reviewing a lot of papers for international journals, where we found that type of mistakes are there. We ask the others to rectify those things. So what we have done is that pressure torsion, zero to another side and positive side. Both sides we have evaluated the mechanical properties. Wicker micro hardness test we have done clearly, and with different turns like quarter turn, half turn, 3/4 turn, 1 turn, and 5 turns. As I said earlier, after 5 turns there is no. If you see very carefully here, 1 turn and 5 turn, it is giving almost near the same properties of 75 to 76 hardness values, and in the center it will be less. Why? Because the strain is taking place at the edges of the sample. That's what you can find. The edges are giving more micro hardness compared to the center of the sample. And by using ball indentation technique, and by using the particularly all these samples, since it is a 10 diameter, 1 thickness, which has been reduced to zero point 0.8 thickness, you can see that the strength, it is increased up to 400 MPa. This is for aluminum 2 silicon 0.25% scandium. This paper with my colleague at V. Rajnikant at NML Jamshedpur, we have published this paper, uh, and we have given the reference in the bottom. And next one.
Yes, sir.
So it is not on the question of aluminum 2 silicon alloy. We have done the aluminum 2 silicon 0.25% scandium, and you can see that beautifully. I think the grain size, how it is reduced to less than micron and nano size, how it is going. You can see the beautiful grain sizes which are very, very less. And in the right side, you can see the dislocation pattern, how dislocation pile up is taking place. And it is making different grains. You can see there are three grains in the dislocation loop is taking place. You can measure also what is the dislocation distance, it can be measured. And aluminum 2 silicon after 5 tons, it is giving 0.38 microns, that is less than 1 micron. And aluminum 2 silicon 0.25 scandium after 5 tons, it is giving 0.15 micron. That is almost like half of this one only. So, as you are increasing, the influence of scandium content can be understood from this images. And if you talk about mostly these mechanisms, the micro mechanism and substructure formation during HPT in aluminum 2 silicon alloy are similar to that aluminum, with dislocation cell formation and reasonable recovered substructure, whereas aluminum 2 silicon 0.25 scandium, it is non-homogeneous, and they are array of non-equilibrium boundaries and dislocation tangles within the grains that can be measured when you are having aluminum to silicon 0.25% scandium Li. So you try to understand not only the influence of high pressure torsion after 5 tons, how it is happening, you can understand the influence of scandium content also in this one. This is the work what we have published. Next slide.
Yes.
Whatever we are showing the images, whatever work we have done, and please try to understand that for most of the, since 1 minute,
Okay.
sir, I'm in giving namaskar ji. Can I give a call after 9 o'clock? I'm in lecture. Okay. So, aerospace applications, when you are talking about, as I have given earlier, that what are the different aluminum alloys. Here you can see that 7475 Li, that is the commercial aluminum zinc magnesium alloy. This is being used for aerospace application, and you can see that what is the zinc and magnesium content in this one: 6.2% zinc and 2.6% magnesium. This is the what we are 7 is for the series of zinc magnesium 0.4% means 57475 Li. This is the high strength aluminum. You talk about 1000 to 8000 series, the highest strength where you get is for aluminum zinc magnesium alloy only. Since you are having a little zinc in this one, you are getting some corrosion problem in this one, and this material is extensively used. But since it is having little limitations, wherever some applications only we use aluminum 7475 alloy, not everywhere. We thought that we take already the 747, which is a high strength aluminum, considered as a high strength aluminum alloy, and trying to understand compared to other alloys how this is better. And this alloy, if you homogenize this alloy and you do the high pressure torsion, what type of strength properties can be improved? Those studies we have done, and you can see that these commercial aluminum alloy, whatever we are doing 7474 alloy, it is processed with high pressure torsion, and I will be presenting the mechanical properties of these alloy after high pressure torsion. Next slide, please.
Yes.
So this is 7475 alloy. We have processed with different tons, half ton, 3/4 ton, and 2 tons. You can see that there are 4 graphs, and the bottom one graph is like micro hardness tester. You have used Vickers micro hardness. It is coming around 160, which has been HV, that is Vickers hardness. I think hardness, you people must be knowing that our resistance or indentation is called the hardness, and all hardness you are having a units. For simplicity, they are putting as HV, HB, or RC or RB, but it is having a units like Newton per mm square. Why? Because the Vickers hardness number VHN is equal 1.854 n by p by d square, where p is the load and d square is the diagonal length of d1 into d2, that is d square. P by D square, that is Newton by mm square, that is megapascal or gigapascal. So every hardness is having the units of MP or GPa, but for simplicity we call it as a 210 HV. That itself it shows that it is having that much load by area, particularly this one. So when you have processed with different tons, how the hardness is getting changed, you can see that where is 160 and where is 220 HV. There is a drastic difference between center to edge when you become the distance between the average micro hardness versus distance from the center of the aluminum 74 is presented here, and all 7475, that is aluminum alloy 7475 processed by 3 tons is presented here, and there is a drastic difference in the micro hardness values. Next slide please.
Yes,
So
sir.
7475, if somebody is interested to work on these alloys, typically you are going to have a lot of strength properties. That is the properties you can see here, whether the yield strength or you are talking about the UTS values, wherever the open circles are there, those are the edge, and wherever closed this thing are class UTS at the center in the bottom. The square open is called yield stress, and filled square is yield stress at the center. So a center will be having the lower hardness values or strength values as compared to the this one. Now you can see that we have almost more than 1000 MPa yield strength we have got for this material, which in can never imagine that in aluminum alloys you can get such a high level of strength in MPa. 1050 MPa yield strength is very, very, very high. Even steels also you may not get that much high strength. So we have done extensive work. We have shown this one. We have published this work, and by using different HPT tons up to 3 tons we have done, and we have carried out the micro hardness values, and very nicely we have presented this one. I think this results is very capable, and sigma process, I think those who are using Excel or Origin, there is a sigma uh, Excel sigma processing is there, software that has been used here. You can use any software whichever you like to make such a good slides, good graphs in this one. Next slide please.
Yes.
Now, let us see the microstructure observation, how it is done in optical microscopy and SEM images. This is the microstructure in as received condition. You can see that in optical microscopy, if the micron bar, it is given something like 8 mm is equal to 10 microns. The average grain size, it is something like 40 microns it is there, the average grain size in 7475 Li. And both optical and SEM image we have taken, we have measured the average grain size, we have calculated, and it is coming prior to HPT, it was 40 microns. And you can see that this was published in Journal of Material Science in Material Science. Why? Because one of my PhD student, Deepak Patil, who is working as a faculty now, associate professor in KLE, and I am presenting all his work only now here. In fact, I am the guide, and the Professor Kori, who is the Vice Chancellor now in Open University, Central University in Anantapur, he is the co-guide for Dr. Deepak Patil. And we have published this work in not only in the Journal of Material Science, we have published in some conferences also, abroad conferences. And whenever we do some work, interesting work is there, I made a compulsory that all the PhD scholars, research scholars, PhD students who are the faculty members, they should go one international conference in 4 years or 3 years of research time. They should present in an international conference, and they should get the idea of what other people are doing, and you should try with exchanging. Suppose if you participate in a virtual mode, I don't think you are going to have lot of questions, but if you go personally and present this type in the abroad, not only you get I think I have a interesting story when I sent my one of my student for one country. Why? Because when he is doing the PhD work on composite materials, aluminum composite materials, he requested me that I advise him to go and present this work. The boy is very good and very sincere, very honest. So he suggested me that, sir, I wanted to go abroad, and there is absolutely no problem. Then I requested him to go one conference in China and present. Then he said that, sir, I don't want to go to China and present this work. This is before Corona time. Then I requested him, why don't you go to Los Angeles? There is a conference in processing of aluminum alloys. So why don't you go and present that one? Then he said, sir, I don't want to go to China and present work. Then he says, I wanted to go to Chicago. Then the conference, which is on aluminum alloys, that the date was over. Then I requested the organizers. Then they accepted our invitation and our request, and they advised to come and present the paper. So I asked this boy to go and present. He went to Chicago and presented the work. Off the record, I made the slides for him, very beautiful slides, more than 10 or 15 slides, and he went and presented this work. Then after coming back, I asked him, how many visiting cards you have exchanged? Then he told he did not get any visiting cards. He has not taken any visiting. He did not meet any faculty members. Why? Because the fellowships, whatever are available in the India to grow and present your work, those are all really useful. Earlier, we are thinking that finally, I asked him, why did you choose this Chicago only? So finally, he told that, sir, my sister is there in Chicago, so I wanted to go and present this work. So Swami Karyam, Swakaryam, Rendu Avalani, he went to Chicago, presented his work, and whatever the photographs he brought is his sister family, a lot of beautiful buildings and other things. Then I told you the purpose of going in international conference is not meeting your friends and relatives. The purpose of going and presenting your work in an international conference is to update your knowledge, trying to have some friendship with the faculty members on similar area. Why? Because you are supposed to go and give your when you are doing the PhD work, you are supposed to go VTU, Visvesvaraya Technological University, whether it is a Andhra University or Nagarjuna University. You are supposed to give minimum 6 to 10 references from abroad and in India examiner list. So unless you go and present your work in abroad, you don't understand whether really you are doing good work or not. You don't understand. And I am very happy to inform that 2015 I went to China and presented our work, where I was a session chairman. I think how many people in abroad going abroad and chairing a session there, very few people are there. I think I am one of the luckiest person in this one. This paper was published in Journal of Material Science. And next slide, please.
Yes.
And continuation of this one only on high pressure torsion of how it is influencing the microstructure. You can see that a grain deferment has happened, and high density of dislocation. I think if you see the image A, you can see a lot of dislocations are a high density of dislocation can be observed. And in the bottom figure, when you are observing these, most of the grain boundaries after two turns are ill-defined, and they correspond to the non-equilibrium grain boundaries. These are particularly a characteristic microstructural feature of material processed by ECAP HPT. I think if you see most of the images processed by ECAP or HPT, you can see similar type of images or TM micrographs. This is the TM image of 2-ton HPT processed aluminum 74 aluminum zinc magnesium alloy. I think you can see that most of the figures, it looks like that only. Why? Because you get a lot of non-equilibrium grain boundaries, and you can see such type of images after HPT. Next slide, please.
Yes.
I think what we'll do is, what are the observation we have made on high pressure torsion on 7475. I wanted to give you some of the conclusions, or I will not make as a conclusions, why? Because a lot of work can be done on this one. Some of the observations what we have made on high pressure torsion on aluminum 7475 is the hardness values increases as in the center of the sample is very less. At the edge of the samples or the discs, what why? Because you are taking a 10 disc only, the values remain low in the central region, and at the edges it is high. The absence of hardness homogeneity is due to the limited extent of HPD processing through a maximum of 2 tons. So we have done only 2 tons here, and we wanted to see that how HPT is useful for making. That's what strength also we can see that we have reached a 1050 MPa. And processing by HPT through 2 tons reduces the grain size at the edge of the disc from an initial value of 40 microns. As we have seen earlier images also, the grain size in whether you take optical microscope or SEM images, and when you have taken the as cast material, it is giving almost like 1040 microns. And after HPT of 2 tons, the average grain size has come to 70 nanometers. And not only getting such a low, very less grain size of 70 nanometers, we have got ultimate tensile strength of 1050 MPa at the edge after 2 tons was attained. This is the work what we have done for high pressure torsion on 747 line. I think uh, Dr. Prasad, you can next to go this one. I think over. I think
HPT. Yes, sir. I moved on to next slide.
okay. I'll show you another some of the slides left over on high pressure torsion on aluminum 2024 Li. Why? Because why we have chosen 2024 Li also I wanted to mention here. For any aerospace application, particularly we are working on Saras aircraft system, where the skin material, most of the stringers, most of the engineering parts of aluminum alloy, they are made with aluminum 2024 alloy only. This is the material which is aluminum copper system, 4.5% copper system, which is known as duraluminum. And we are using 2024 or 2014 Li extensively for our Saras applications. And when you have done the high pressure torsion, how it is influencing, particularly this Li is available. If anybody wanted 2024 Li, they can approach us. We can send you free of cost this material. We have extensive sheet form we are having, and billets also we are having, and we are doing extensive work on 2024 and 2014 Li. And if you see the SEM images of this one at low magnification, high magnification, you can see beautiful grain boundaries of where AL4CU is precipitated along the grain boundaries, and you can see the grain boundaries, and beautiful images have come, SEM images in as received condition. Next slide, please.
Yes, sir.
So before understanding anything, you are supposed to have the grain size reduction, how it is taking. Now, similarly, this AL 2024 Li, that is duraluminum Li, when which is extensively used for aerospace application, we have used the automatic ball indentation, and the center edge for all the tons, quarter ton to 5 tons. This is what is the research work we have done. You can see that YS and UTS how it is changed. The UTS is going up to 1160 MPa with n value of 0.09. N value as the it is increasing the values of YS, the N values decreases. And at the edges, you can get the UTS of 1160 MPa. This is tremendously very good results, which we have published also. And ABA results of I have already explained how the ABA is done for this high pressure torsion samples when the sample size is very small. How you can do the ABA and get this information. Next slide, please.
Yes, sir.
And what are the results we have got for this one? We have put it in a pictorial way by using the sigma plot, sigma plot analysis, UTS at the center and UTS at the center at the edge, and YS at the edge and YS at the center. You can see that UTS at the edge is comparatively higher than all the values. YS is comparatively less, and this is as expected. That mechanical engineers design aspects when you are studying, you should you should proud that London Eye is being developed by mechanical engineers, where 1 ton, if you do the giant wheel, you can see whole city of London. And till date there was no accident, and there is no accident, and people are very happy. Why? Because the uh, uh, ratio, whatever factor of safety, whatever it is measured, is 1.5. And for aerospace application we take more than 1.5, that is 100 MPa is required. You take 175 or 200 MPa, that is a two factor of safety is for aerospace application. If it is engineering application, 1.25 to 1.5, this is the factor of safety whatever we are considering. And for in general aerospace application, the factor of safety should be higher. And whenever you are designing any aircraft, this thing, what is the main requirement is you should have a safety of the passenger is the most important. Then it should be economically viable, the rate should be very less, and you should have a comfortable journey. This is what when you are doing any, we are having almost 20 divisions in our laboratory, and everybody is working on different aircrafts, and Saras or Hansa or NM5, and we are mainly looking after the material properties only. Next slide, please.
Yes.
I think uh, after understanding this one, uh, whatever the again we are taking the uh, TM images of aluminum 2024 only, and you can see that the dislocation type pile up is how it is taking in left side image, and this is after 5 tons of HPT, that is high pressure torsion of same aluminum 2024 Li, where we got the ultimate tensile strength of 1160 MPa, and after 5 tons. And SADP pattern also we have taken, and you can see the atoms how they are arranged. You can find out what is the distance between each atom and what is the d-spacing. All these things can be measured. I think those who are having experience in TM, they can easily understand that if it is a still, if the atoms are coming to near, not like a particularly crystallite size, now there is a deformation has taken place. That's what there is a difference in the atom positions. Now if further if you do it, you can find like a line where from SADP pattern we can clearly say that whether it is a crystalline material, whether it is a severely deformed material, you can easily tell by seeing the TM image. Next slide, please.
Yes.
I think I'll quickly go through on RCS. Why? Because 9 o'clock we had 7 minutes left over. I'll complete this one afterwards. If anybody is having questions, they can raise. And we have done extensive work on repetitive corrugation state RCS method. I think whatever method you are telling, I have given some of the works. Why? Because we know what is to be done, and we have given RCS for another fellow in Hubli. He has done extensive work on R. I should be thankful to Dr. Prabhakar. He is a associate professor now. Once he has completed this one, he got a good project also on RCS, and he is doing extremely good work. I must congratulate him for doing the work on RCS. Initially, we have done with the press. Now we have developed a unit. 1 minute. Hello. Can you call after half an hour, please? I'm in a lecture. I am in a lecture. So this work on RCS. Next slide, please.
Yes.
So this is the work which I have explained earlier also, that you can take the sample, and by putting the sample with the corrugation, and again you can make the straighten. And we have taken different type of aluminum material, pure aluminum, aluminum 0.25% scandium Li. We have done the extensive work on this one. We have published this paper, and the hardness also we have calculated. And the reason we have given, as you are increasing the number of RCS process, the hardness is also increased. Why? Because this is due to the shear strain introduced during RCS as compared in the other processes. the strengthening effect in RCS versus rolling. Conventional rolling process we have checked with aluminum, 0.25% scandium also Li we have taken. Next slide, please.
Yes, sir.
This is the RCS. I think I need not to. I would have shown a beautiful image, HPT RCS process. You can see this is a very useful machine where only the length of the sample should be high, whether it is a 10 mm by 10 mm by 500 mm length samples, and you can do by 10 mm, 8 mm, 6 mm, 4 mm, any type of sample you can bring. You can do in one machine itself. And now we have developed another machine. I think next slide you can see that. Next slide, please.
Yes, sir.
This is the initially what we have done when we have started this RCS work. It is something like a sugarcane technology. We have used sugarcane, how it is behaving. So we have put top view and front view here. We have keep the sample so that it will become initially a corrugation type, and after that there is a plain rollers where you get the straightened samples. Next slide, please.
Yes.
This is the one continuous process where you can see that we have now this machine is available with us. If somebody is having 8 by 8 by 120 samples, they can send it to us. We can process this one by one pass, two pass, three pass, four pass, and we can do very nicely process this one, and you can evaluate the mechanical properties, and we can jointly write some papers on this one. Any type of material is there by 8 mm by 8 mm or 6 by 6 by 120 mm. If you are having, you can send the samples. We will do the processing and send it. This is the continuous RCS system we have developed. Now, presently, it is available in our laboratory. Next slide, please.
Yes.
This is the work what we have done for aluminum 2024 with rotation and without rotation. So one thing what we can do is you can continuously do the RCS, or you can flip into whenever you are doing one pass, you can just change the sample, and once it becomes straightened again, you can do the corrugation like that. We have done for as cast without rotation, and with rotation we have done. With rotation, it is giving 470 MPa ultimate strength and 240 MPa without. This is 2024 with scandium content and without scandium content. As cast, you can see that 70 MPa yield strength is there, which has been increased to 240 MPa. That is almost like 3 times. The hardness levels also you can see 45 HP at 0.5% load. It has been increased after with rotation. When scandium content is evolved 180 MPa, it has been in 180 HV. So this is one of my MTech student from NIT Calicut. He has published this paper in Material Science and Engineering A in 2012. He has published this work 10 years back. Next slide, please.
Yes.
I think what I wanted to mention here, I think I will close this one by it is not the question of doing the work only. You are supposed to have uh, friendship with other people also, where we went bulk nanomaterials 2009 conference. We went. You can see in the center Professor Manna of IIT Kanpur director. Now he is a vice chancellor of PIT Mishra, and you can see right side corner Professor Atul Choksi, and you can see in blue shirt where I am sitting in the left side top corner, and one of the IIT faculty, IIT Chennai faculty is the center, and at the left extreme Professor Rolson Valley, whose 60th birthday we have celebrated there. We had a nice breakfast function, so we are supposed to have like this. And in 2011 Nanjing, we have gone for an fifth international conference. Every 2 years we are supposed to do it. Last year we were supposed to 2020 we are supposed to do in Bangalore. Due to corona we could not able to do, but 2023 February we are conducting the same conference on international conference on nanomaterials by severe plastic deformation. I think whatever the Dr. Prasad has made this FDB program on nanomaterials. I think I am talking about international level, what nanomaterials people are doing by severe plastic deformation. I think if you can see the photograph very closely, left bottom extremely, I can sit in the front row. I am at the left side corner, and right side corner is my host, Professor Terence Langdon, and Nanjing, wherever we have gone to China. He is the secretary of that conference who is sitting, and fourth one is Professor Rolson Valley, and the center of that one is from Australian lady, and French man who is sitting at next to him is a French fellow, and another. So I can tell the names of the faculty members also. You are supposed to, if, when you are working on some area, you should know who are the experts all over the world. This is what is request to all the faculty members. In 2011, we have taken this picture, and 2009, and we go on having images. You should have a record of like this. I think with this, Dr. Prasad, I wanted to conclude this one. Why? Because 9 o'clock is already. Let them
Yes,
ask some questions. We can give the reply.
sure, sir.
Can you close
I
it?
request the participants to raise their questions on the discussion so far happened. Especially, it's good for mechanical engineers and metallurgical engineers both.
Both the
Others,
people, they can ask any questions.
Good evening, sir.
Good evening. Please ask your question. Please tell me.
Sorry, you have mentioned SPD process like ECAP.
Yeah.
So after doing ECAP, is there any chance to develop internal stresses in the member?
I didn't understand. After doing the ECAP?
Any chance to develop internal stresses?
Yes. You are absolutely right. Whenever you are doing any severe plastic deformation, you are going to have some of the stresses in the material. Okay.
Yes.
But that stresses to be removed from the sample, if you are doing some annealing treatment or anything, the grain size will increase. Okay.
Okay.
So, with the limited stresses, where it can be used, if you can understand the application, that will be easy and it can be considered. The stress levels will be very, very low.
Okay, sir. And another thing is the strength of the membrane is depends upon grain size or alloying elements, sir.
Both.
That means
Alloying elements is having a like addition of scandium is responsible for decreasing the grain size. One aspect. Another aspect is by doing the severe plastic deformation, you can further reduce the grain size. That is another effect. So there are two effects. One is by addition of alloying elements. Another one is by doing the severe plastic deformation.
and another thing is the dislocation is depends upon what parameters, sir, actually.
Dislocation generally when you are having any material, okay.
Okay.
See, the atoms are arranged in a regular fashion. They are sitting in one position. Okay. You are not disturbing them. But when you wanted to do some processing of that one, internally, whatever the atomic structure is there, they are all sitting and quite good. They have interatomic cohesive forces are there. They are sitting. But you wanted to try to disturb them. When you want to disturb them, they oppose these forces. This opposing the forces is nothing but your strength, nothing but your hardness. You understand?
Okay, sir.
So whatever the dislocations you are mentioning, those are all, in fact, those are all atoms. If you can see my hand here, they are all arranged like this. Now you want to deform the dislocated. The position has been dislocated from one place to another by applying some of the forces. You understand? So when you wanted to oppose these forces, you require some strength. That's what these are all called dislocation, whether it is a screw dislocation, whether it is a edge dislocation. We can see from the TM images, we can find out what type of dislocations are there. they have been dislocated. Earlier, they were sitting in Aram one place, and now they have been dislocated. Those are all called dislocations. So one chapter is there on dislocation itself.
Okay, sir, but the dislocation is also, I think it is prevented by precipitations.
If you have the precipitation, that's what when you are understanding the overone looping or precipitation hardening, when you are doing all those things, the dislocations can cut the precipitates. They can overlook these precipitates and go. That is called overone looping. Otherwise, they can cut the precipitates. You get the strengthening effect by these two methods. Did you understand, Dr. Veeraya?
Yes, sir.
Okay.
And also, if, for example, if I have done friction stir processing or friction stir welding for a material,
Okay.
after that, if I do this ECAP process, is there any advantage for membrane?
No, no. Why? Because once you have done the friction star welding, you are already generating a nanostructured material in that one.
Yes, sir.
Okay. Now,
Yes.
why do you want to go and do the ultrafine grain structure? You are already having a nanostructured in this one. If you are doing by ECAP method, which is mentioned for only ultrafine grain size, there is no use. You are already having a nanostructured in this one. What I can suggest is whenever you have done the friction star welding, you are
Okay.
going to, what is the advantage of friction star welding is you are going to generate the nanostructured material,
Okay.
and you are limiting the heat affected zone. Whereas in all other commercial TIG or MIG welding or any process you are doing, you are having the large size of heat affected zone where the cracks are initiated and propagated and failure happening. This is the only method in friction star welding where you are minimizing the heat affected zone and having almost like a nanostructured material, so that you don't fail any samples after friction star welding.
Sir, if I do this ECAP process prior to friction stir welding, is any advantage?
Absolutely, there is no use.
Okay, okay, sir.
No use, no use. You have to do the. That's what one is ultrafine, one is nanostructured. You know, you define which is you wanted.
Okay, okay.
But primary understanding about if you are doing the ECAP process, and one Australian lady, Castro, she's a Russian lady who settled in Australia. What she has done is ECAP after 4 passes, she has done the rolling work.
Okay.
And she told that there is no much difference after rolling work also. That
Okay,
type of work you can do it.
okay, sir.
Okay, okay.
And also, sir, you mentioned that HPT, right? High pressure torsion.
Yes, yes.
Actually, in that, I have observed that at the center, the hardness is almost as received alloy.
Yeah, yeah, yeah. Center, it is not having much influence, but whereas the edges, it is you are getting a high strength and high hardness in the edges.
Actually, even the edges also, there is a large difference between yield strength and ultimate strength, sir. Actually, we need to bother about yield strength only.
Yield strength only. That's what you need not to mention about the UTS values at all.
Okay, okay. Uh,
This is for the purpose of publishing the papers. We have shown the UTS and YS values, but
okay.
if we are going for a design of any engineering components, YS is sufficient.
Yes, sir. Yes, sir.
I wanted to show you ECAR, which is JNTU Vijayanagaram is having that facility. We have done some extensive work. I think, I don't know, I could not able to show that work. ECR is another rolling, particularly when you are having a conventional rolling. If you are having an equal channel rolling, how the mechanical properties are improved. We have done that research work. We have not published. I wanted to show that results. I could not able to show Dr. Srinivas Prasad.
Yes, sir.
The time is limited, so I have not shown that ECR results.
We shall have it in another session, sir. Another wonderful
Yeah,
session.
yeah.
Okay, sir. And another thing is, you have mentioned that there is a plenty of work is in aluminum lithium alloy.
Yes, yes.
What about the applications of this metal alloy, sir?
All aluminum alloys are for aerospace application only. You are replacing the aluminum 2024 alloy with aluminum lithium alloys. Why? Because 2024 is a generally considered as a non-weldable material. There is no word called non-weldable material. Everything can be welded, but you don't get the required mechanical property. That's what it is called as non-weldable material. Why? Because you are having Al4Cu precipitates. Okay. Those
Okay.
are all brittle in nature, so you don't welding is not good for aluminum copper system. So it is not that non-weldable material. It is you can do the welding, but you don't get the
Sir, can we do this friction stir welding for this 2024? Is it
Hmm.
possible?
Yes, yes. Our colleague Mr. Suresh, he has done extensive work on 2024 and 7475 on friction stir welding. You can use the conventional milling machine only, and you can do the uh, FSW work on this one.
Sir, how did you measure this strength at in HPD sample? You
Uh,
have measured strength at the center and periphery, and
yes,
you have
that's what
mentioned
I
strength.
told you. ABA technique is used if you are having a small sample of 10 diameter by 1 thickness. You can, by using the ABA technique, automated ball indentation technique, a steel ball will be there with the 0.2 diameter. You load it,
Yes,
unload it, you can get all the mechanical property. That's what is the technology has been transferred from NML Jamshedpur.
yes, sir. That means without that API technique, it is not possible, right?
No possible. Otherwise, you have to make a small sample of from 10 diameter only and trying to put in your machine. All the machines will not be having. Why? Because your gap is only 5 only.
Okay, sir.
Very difficult.
Sir, and one more thing I couldn't understand. I think we have series from 1 to 9, right, sir?
Yeah,
For example, I have 5083 LI.
yeah.
What that series indicates, sir, 5 stands to 083.
That's what it is. A 5,000 means 5 stands for magnesium. Okay,
Okay, sir.
0.08 stands for silicon content, and last one is by heat treatment method. Whatever the heat treatment technique they have used, whether it is as cast, whether it is a heat treated condition, those parameters you can understand very nicely. If you tell the any LI 2024 or 5083, we can tell about what conditions it is there.
Sir, actually, I'm doing on 5083 and 7075 only,
Okay.
but I couldn't find what is this numbers indicates actually.
Okay, okay, okay.
Uh,
If you can give that number, I can tell you. I can send you. That's what you can take the email from Dr. Prasad. Whatever the doubts you are having, you can put it in this thing. Now I am doing a lot of review process also. I can give all the answers for you. Absolutely no problem.
okay.
Yes, sir. We'll share the your information, your contact details through the
Yeah,
FYP.
Karodi2002 at yahoo.co.in. If you can
Actually,
send the email.
I knew that, sir, because I have published one article with you only. I am from
Okay.
MEGR College, Vijayaram.
Oh, okay, okay. On
Sudhakar Garu.
welding one or other one?
Yeah, TIG welding only, sir. 5083 and 7075.
That is a TIG welding. Okay.
Now I'm doing friction stir welding on same alloys. No?
Okay, okay. You can do that one.
Yeah, it's a comparative study on TIG and FSD.
Okay, okay.
Sir, thank you,
Any more questions?
Thank you. Thank you, Dr. Viraya.
sir. Thank you, sir. Thank you.
Thank
Any
you.
other questions from other participants?
At least I'm happy Dr. Viraya is having a lot of questions and he wanted to. Why? Because we have worked jointly for his work on TIG welding of some of the aluminum alloys. So we have provided all aluminum alloys from here. We have done the TIG welding also. We have provided to him. He has done some mechanical property evolution. We have published it jointly. That's what he is having a lot of doubts. Very happy
Yes.
that he is having doubts.
Sorry, sir. Actually, I'm not a doctorate one. I'm pursuing in PhD in Andhra University.
Okay, okay, no problem, no problem. One day you will become. Don't worry.
Yes, sir. Questions are
Thank you for your.
important. Without
you.
questioning, there is no knowledge gaining.
Yeah.
Okay, sir. Respected sir, in the beginning of the session, you wonderfully addressed that before advising, learn yourself and practice, experience yourself. Then only
Correct,
we will
correct.
come to real things. Wonderfully said, sir. And also, it is interesting to know that 8 conferences were held on severe plastic deformation and on this grain refinement to get ultra fine grain uh, processes by various SBD techniques. Wonderful explained that ECAP technique, RPT and HPT, equichannel angular pressing, high pressure torsion, and repetitive corrugative and strengthening techniques for obtaining this ultra fine grain structures. And some other synthesizing techniques, an automated ball indentation system for very small size specimens to understand characterize the properties. So very well explained, sir. On behalf of Department of Mechanical Engineering, JNTU Gurjada Vijayanagaram College of Engineering Vijayanagaram, all the faculty members and participants, I would like to extend our sincere thanks, and we are very much thankful for your valuable and expertise and experience sharing with all of us today. Thank you very much, sir, for being with us. Thank you very much, sir.
Sir, if you don't
Thank.
mind, I have one question. Venkateslu, sir.
చెప్పండి.
Are these images exactly give, sir?
Where?
That software you have mentioned that one software is there, Image J, I think.
Image J. Image J, you go to the Google and write Image J software.
Okay.
It is a public domain software. You can download and it is freely available. You need not to pay any amount. Continuously, you can work on that one. For
Okay.
doing the particle size from the image or
Okay, sir.
volume fraction of the images, that is a very good one. People should use that one extensively.
Okay.
Thank you
Thank
very
you, sir.
much. Thank you.
Thank you.
Thank
Thank
you very much,
you,
sir.
Prasad.
Thank you, sir. And okay, sir.
Thank you, Dr. Swaminaidu, for contacting me and